up to the practical and simulation that you need to do. I'll be issuing the assignment next week. So, filter is a two-port network that allows selected frequency signals to pass to its output whilst rejecting, or in brackets attenuating. It does that by attenuating So, how do we achieve variable attenuation? If you remember back to last week, when we were creating attenuators that had a fixed attenuation, we said they needed to be constructed from a circuit of resistors only, because resistors, the resistance is independent of frequency. So, the basic passive filter is designed using a combination of inductors and capacitors, as these components vary their impedance as frequency changes. So, leading back to the science that you did in the first year, this shouldn't be totally new to you, but the impedance of an inductor is equal to 2 pi times the frequency times the inductance of that inductor in henries. The impedance of a capacitor is 1 over 2 pi times the frequency times the capacitance of that capacitor. What that means, this one, if we increase frequency, we increase ZL. So that one, impedance goes up as frequency rises. Consequently, impedance will go down as frequency falls. With the capacitor, increase F, decrease ZC, the inductance of the capacitor. So in terms of changes in frequency, the impedance changes in opposite directions for these two components. So as one's going up, the impedance of one goes up, the impedance of the other must come down for any given change in frequency. Okay, so that using those two components in a simple two-port network, we can design a fairly simple passive filter. Right. So, different types of filter. First of all, and some of you are going to build one of these, a low pass filter. This is a filter that's designed to have or allow frequencies below a chosen design frequency, which is called the cutoff frequency, F little c, to pass whilst rejecting frequencies that are above FC. So we've got this little diagram here. Here's our FC in there, and this low pass filter will allow anything between 0 and FC to pass through. Okay, but once we hit the cut-off frequency, the idea is that it attenuates then, it reduces the signal. In actual fact, in a real filter of the kind of design you're going to build, doesn't fall off as a straight line like that. It does that. Okay? We can build that filter from either a pi-type design with 2 shunt capacitors and 1 series inductor, or we can build a T-type with 2 series inductors and 1 shunt capacitor. Either way, and I'll go through how that achieves that variable attenuation in detail in a few slides' time. Okay. Generally, we would choose, in terms of do I make a pi or a T, here you would choose the design, in my opinion, unless there was a pressing need not to, that only had 1 inductor. Because the reason being is the inductors are likely to be a bigger component, taking up more space on any particular board, and more success, and also likely to have the wider tolerance range as well. So if you're building a low pass, you're going to be building a low pass pi type because it will only have 1 inductor. Yeah. So the operation of a low pass pi design. The shunt capacitors are chosen to have a high impedance at frequencies less than FC. So these two, high ZC, the series inductor was chosen to have a low ZL. Yep. So what happens is, you don't stop at all, a tiny little bit of current goes down through that capacitor. The biggest majority of the current going in at the start goes through the low impedance inductor. Perhaps a little bit more current goes down the second shunt capacitor, but not a great deal, and a large amount of current comes out of the output because it's in the pass band. Yeah. The design will also have at higher frequencies, so it'll be designed so that above FC we'll have a low-ish ZC for those two, and a relatively high ZL. So for the same current in, a small portion will go through the inductor, a large portion shunted down the 0 volt rail. Most of that shunted down there, and a very, very small portion out to the output. That's in its attenuation band, i.e. at frequencies above SC. So the physical value of the components doesn't change. It's the fact that they react differently at different frequencies that gives us the filler and action. Okay? So in cases, the further you go above FC, the lower this impedance cut comes, and it's why you get that ramp cut off rather than a straight line. That's because the change is gradual as frequency increases. Okay, everybody all right with that so far? Moving on then, Operation of a low pass T. Ah, okay. Low pass T. So in this type, at frequencies below FC, we have inductors that have got a low ZL there and there, and a high ZC. So again, for the current going in, most of it goes through the second inductor, a small current down there, and off to the output. Here we've got a high ZL and a low ZC. So this blocks a considerable amount of the current, of which the majority goes down through there and only very little out through the output, because that blocks even more. Yeah, so I get that filtering action with 2 series inductors and 1 shunt capacitor. So that's the action of the 2 different types of low pass filter. If you're building a low pass filter for your assignment specification, you'll be doing that pi type design, because it's only got 1 inductor in it. Okay. Second type of filter we'll need to consider, some of you will be making these, is a high pass filter. So this is one that's designed to allow frequencies above a chosen design frequency, the cut-off frequency, to pass while rejecting frequencies below. So here's FC, here's the pass band that carries on forever after that. Okay, anything below that frequency is attenuated, and again, in reality, it's not that sharp cut off, it's a roll off like that. And again, we can have a pi type design with 1 series capacitor, 2 shunt inductors, or a T type design, 2 series capacitors and 1 shunt inductor. And so if you're making a high pass, you'll be making a T type, it's only got 1 inductor in it. Okay? There may be an odd one of the designs we got in the list that you might end up using 2 inductors, because you need to connect 2 in series or parallel to get the value you want. But other than that, in general, you'll be working with 1 inductor. All right? Any questions so far? So, what's the operation of these? At frequencies above FC, these 2 capacitors have a low, give a low ZC, and that 1 inductor high ZL. So the current coming in goes relatively easily through the low impedance capacitor. A little bit may well get down the inductor because it's not perfectly shut off. Quite a lot will come through there and pass through there to the output, so you get a reasonably high output level. Note there will always be some attenuation, less and less as the frequency goes up, but there'll always be some. Okay. In here, low ZL, high ZC. Therefore, the capacitors tend to block the current. The low ZL shunts most of it down there, and very little goes through to the output. So we're in our reject band, our attenuation band. Okay? Well, no, because you need the combination of both to get the, yeah, they work with each other to provide it. You could do a design, you could probably do a very simple design where you just had one of each, but what you won't get then is you won't get the impedance matching that you need. Remember the impedance matching from, so you've got, when you work, if you do hand calculations for this, you end up with a value for overall, let's go back to, if you end up with a value for overall capacitance, and in this circuit, the two capacitors are in series, so you've got to put twice that amount in because capacitors in series half the value. Yeah. Where they're in parallel in the other circuit, in there, hang on, no, this one, two capacitors in parallel, so you'll calculate a total value for C, and then you'll put half of it in each of those two places. And that's about getting the input and output impedances to be the same value. Alright? Yeah? But you can't make a filter with just one component, no. Alright? So that's that one. I'm not going to label the point and go through the high-pass pi design because you know why we're not doing that. It's two inductors and the principles is just the same as we've just gone through there. So I'm going to leave that one. And move on. Right, for completeness, there are two other basic filter types that you could come across. You're not going to build either of these, but there are. What's called a band pass filter, two cutoff frequencies, and these filters allow frequencies between F1 and F2 to go through and reject those frequencies either side. So it allows those frequencies through. An example of a T band pass filter, you can see it's got both types of components in each half. It's like a combination of the two circuits, a high and low pass filter, shunt components in series, and the series components in parallel. Okay, so you get an effect where at some frequencies this is the high impedance component and that's the low, and then vice versa as it goes the other side, the other component comes into force. Okay, and then lastly there's what's called a band stop filter. This is where the frequencies between F1 and F2 are actually attenuated and pass everything either side. And notice the circuit is kind of the opposite of what you had there. The series components are in series and the shunt components are in parallel. There's a combination of the two circuit types. Okay? Not going to go through how they work in detail because we don't really have the time. We're interested in the high and low pass filters. Everybody happy with that so far? So, this is quite an important part of what you need to know to be able to do the practical work and understand what's going on with these circuits for your assignment. The rate at which attenuation increases is not vertical but rolls off at a rate dependent upon the complexity of the design. So There are other filter type designs. You're going to be building what's called a constant K type 2-port filter. The simplest one out there, really. There are other designs that will help to steepen that roll-off so it's more vertical. But they're more complex and take more time for us to go through their operation. So we're leaving them to one side. So there's a specific level of attenuation that the cutoff frequency is specified to be. So we've got our, if we look at a low pass filter, we've got a roll off like that, and we need somewhere to specify where we say the cutoff frequency is. Is it right there, or is it? And what it actually is the point here where in the attenuation is -3 dB, or the gain is -3 dB, the attenuation is 3 dB. That's where we specify the point for FC. Yep. So ideally, if you're designing a 40 kilohertz low pass filter, okay, if that's going to be ideal, the attenuation that is given you at 40 kilohertz would be 3 dBs of attenuation. Okay, it's where power out divided by power in is exactly half. You're getting half the power out that you're putting in. Okay. Alternatively, if you're looking at voltage in and voltage out, it's where V out over V in is equal to 1 over the square root of 2. What does that come out as on your calculator? 1 over root 2. Sorry? 0.707. Yeah. So what that's saying there is you'll be at that point when you're putting 10 volts in, you're getting 7.07 volts out at the output. That's specified as the standard for where the cutoff frequency is. Okay. And there is I've got a practical from instrumentation. Got a practical example of where that fits in. In the 405 lab across there, there's some ultrasonic level measuring instruments. What they do is there's an ultrasonic head that sends out an ultrasonic beam down to a target. So that's a target you're aiming for, the level in the tank or something, okay, and it sends that out and reflects it back, and it times how long it takes to do that, and then you program it so that it can, from that time, work out the distance between the two. If it knows the overall depth of the tank, it can work out what the level is and so on. But what that has is a beam angle. And you can buy sensors with different beam angles so that it doesn't encroach on the sides of your tank or any ladders that are going up the side or anything like that. You can buy different beam angles. The way they specify that beam angle is they put a microphone directly underneath and take a level, and then they move it off to the side until they get 0.5 of the power they had there, and that angle between those two is the beam angle. So they measure where the power of the signal being reflected is dropped off, or being sent out is dropped off by a half, and they specify that as the beam angle of that sensor. Okay. So that graph gives you that kind of thing in detail. So here, there's a low pass. This kind of plot has frequency in hertz on the horizontal scale. Okay. Now, what you want to note is that that scale is logarithmic too. So it doesn't go in decimal amounts. It goes in 10 hertz, 100 hertz. So the same distance is 10 times the last distance. Yep. It's logarithmic. This is attenuation in dB. Okay. And there is our passband. We start to roll off, and there's our 3 dB point there, which specifies our FC down there. Exactly the same with the high pass filter, but just turn that the other way round and you roll off and go down the other way. Okay, but you have to have a specified standard of where you define that cutoff frequency is, because we can't have some people picking 2 dB and others saying us at 5 dB. We have to have an industry standard, so that's what it is. Minus 3 dB power. Yep. So, filter design calculations. For the assignment of this module, you're going to be required to build, to design either a high pass or a low pass filter to a specified cutoff frequency. And you'll also have a design impedance as well. Yep. Either 600 ohms or 50 ohms. As with the attenuators discussed last week, also important to have the right termination input and output impedance to match the devices that you're going to connect it to, so we have maximum power transfer. So you're going to have a ZO specification as well for your filter. Okay. So calculations for a low pass filter. To design a low pass filter with a cutoff frequency of FC and a characteristic impedance of ZO, you use those formulae there. So you get the total capacitance you need for the circuit from 1 over pi FC times ZO, and the total inductance from Z over pi times FC. If you were doing a pi type design, which you would be for a low pass filter, you put all the inductance in the series position, and then you put the total capacitance divided by 2 in each of the shunt positions, because capacitors in parallel add together. Yeah. So if you worked out for it to be a 30 microfarad capacitor, you put 2 15s, one in each position, and then a, let's say, 10 millihenry inductor in the series position. If you were to do a T-type design, you'd need to divide the inductance by 2, because the inductors in series, you have to add their values, and then you'd put all the capacitance in the shunt position. All right? So we'll have a go at an example in a little while, so we can see what we get. High pass, here we get the total capacitance again from 1 over 4 pi FC ZO, and inductance by Z over 4 pi FC. If we did a pi type design, we'd put 2 times the inductance in a shunt positions, because inductors in parallel half their values, 2 in parallel half their values, all the capacitance in series. If we'd done a T-type design, which you would do in your case, you'd put twice the capacitance in each series position, because they half when they're in series, and all the inductance in the shunt. Yeah. So although you're going to use some software to actually design your filter, you can also show hand calculations. You've got those formulae should you need and want to do that. All right. So what I want you to do now is, using those formulae, design a T-type high-pass filter with a cut-off frequency of 40 kilohertz and a characteristic impedance ZO of 600 ohms. In fact, let's do a little bit what we did last week. Middle table, right, do 600 ohms. Back and front here, do 50 ohms. See what we get. No, never mind, forget that, because I've got to do it twice then. Do them all the same. 600 ohms, all 600 ohms. Doesn't really achieve anything extra. What we'll do then, like we did a little bit last week with the online calculator for attenuators, we'll have a look and see the results we get with the design software that you're going to use for the filters, which is called LC.